I'm delighted to welcome you all. I'm Kerry Colanisi, and this is the fifth in our year-long series of workshops on artificial intelligence and climate change. Both of these phenomena, artificial intelligence and climate change, are two of the most consequential waves of change that are affecting the globe today. And we are just really pleased that we can bring together some of the world's leading experts from across disciplines to have a conversation with our students, our faculty, our fellows, our staff here at the University of Pennsylvania through this workshop series. As we get started with today's workshop, a few announcements. First, there will be a change to today's program. Professor Michael Mann had been very much looking forward to being here and being part of a conversation with our featured speaker, but has suddenly come down with the flu. So we will be missing him here today and wishing him well. I do want to acknowledge many other centers other than the Penn Program on Regulation, which I direct, that is organizing and sponsoring today's session and indeed the year-long series. And that includes the Kleinman Center for Energy Policy, where we're here today, and we thank them for hosting us here. Also for the Center for Technology, Innovation, and Competition, the Warren Center for Network and Data Sciences, the Wharton Climate Center, and the Penn Center for Science, Sustainability, and the Media. I want to thank all of our staff from the various centers who work so hard to make events like this happen. Especially, I want to thank our managing director, Andy Cooper-Smith, for all that he does for the Penn Program on Regulation and has done for this event. This event is also made possible in part by funding from the Provost's office through the Environmental Innovations Initiative here at Penn, and we certainly thank them for that. Today's workshop, as all of our workshops, is being recorded, and the recording of it will be posted after the event on our YouTube channel at the Penn Program on Regulation. Also, you should know that after the presentation by Professor Schneider, we look forward to hearing from you and having a chance for you to ask your questions or offer comments. If you'd like to do that, please just raise your hand, and we have folks with microphones who will come and find you and bring their microphone to you. So with those logistical and business items out of the way, it gives me great pleasure to introduce now our featured speaker for today's session. Oh, sorry, before I do that, there was one more business item that I needed to mention, and that is it's going to be spring break next week here at Penn, so have a great spring break. But when you come back, right after spring break, is Energy Week here at Penn. And so if you're interested in these issues about climate change in particular, and you're here at the Climate Energy Policy Center, we want to make sure you're aware of Energy Week at Penn right after spring break. Anyway, now it gives me great pleasure to introduce our featured speaker for today's session, who's here to talk about the role of artificial intelligence and how it can be used to generate more precise and decision-useful information about climate and weather-related risks. Tapio Schneider is the Theodore Wu Professor of Environmental Science and Engineering at Caltech and is a visiting researcher at Google. His research focuses on how the climate of the Earth and other planets comes about and may change by changes, for example, in atmospheric circulation or cloud cover. He's been the recipient of many accolades over the years for his work. He was named as one of the top 20 scientists under 40 by Discover magazine. He's been the recipient of the David and Lucille Packard Fellowship and the Alfred P. Sloan Research Fellowship, a recipient of the Rosenthal Award of the University of Miami and the James Holton Award of the American Geophysical Union. He's a fellow of the American Geophysical Union as well, and served recently as a member of the White House Working Group on extreme weather risks in a changing climate, part of the President's Council of Advisors on Science and Technology. To improve climate predictions, Professor Schneider is currently leading the Climate Modeling Alliance, which is developing next generation climate models using AI tools. He joins us today to share with us some of that research and talk about AI accelerated assessments of climate and weather risks. Professor Schneider.
Thank you, and thanks for having me. Okay. Yes, I will talk about how you can use AI to assess climate and weather risks and ultimately make those assessments accessible and useful. I will not do this in a technical way that I thought was not the forum for it, but at least give you a flavor of what we do at Klima and how this can translate into information that I hope you all can use eventually. Why we care about climate change, I think is clear. Global temperatures have risen roughly 1.4 degrees since the beginning of the Industrial Revolution. 1.4, 1.3 degrees, and the last year was almost 1.5 degrees warmer than pre-industrial times. Perhaps that was a one-off. Next year or this year won't be quite as warm, but the trend is unmistakable. We are currently seeing about 0.2 degrees warming per decade or so. This is the global mean warming. What's important to keep in mind is that you're not experiencing the global mean, but you experience local warming and the manifestations of local warming. And locally, the warming we have already seen can be quite different. Generally, continents warm faster than oceans for reasons that we understand quite well, mostly having to do with the availability of water to evaporate. That's limited over continents and limits the warming. Higher latitudes warm faster than lower latitudes. In some parts of the Arctic, we have already seen winter warming of 4 degrees centigrade or so. And on average, in the global mean in the Arctic, you have something like 1.5 degrees more warming than in the global mean. And then, of course, the oceans warm less rapidly. You see less warming than the global mean. That's important to keep in mind. That's just the warming itself is local. And then all the impacts are even more local that you really care about. Greenhouse gas emissions are still rising. They're rising slowly, but they're still rising. You see there was a little dip from the pandemic that we came out of. There was a little dip from the 2008 financial crisis. But by and large, these are CO2 emissions. They continue to rise. So we haven't quite reached peak emissions yet, it seems. But the rise has gotten slow, so perhaps we will reach peak emissions sometime soon. What you need to stabilize concentrations of greenhouse gases is what changes the climate, right? Here is the famous Keeling curve, the Mauna Loa time series of CO2 concentrations showing the inexorable rise. Even in the time of my scientific career, from the 1990s to now, that's 1990s, we were at 360 parts per million. Now we are at 420 parts per million. It's truly staggering rise. To stabilize emissions, just to stabilize them, you need to get the emissions to near zero. So not just peak, but get down to near zero. And we're clearly decades away from achieving that. Emissions haven't even peaked. You all have heard about the Paris Agreement, the various stipulations in that Paris Agreement. There is the statement that we should limit warming to 2 degrees centigrade, and we should aspire to limit warming to 1.5 degrees centigrade. We are already at close to 1.5 degrees. This is 1.5 degrees average over a decade, so we haven't had that yet. From the most recent IPCC report just a few years ago, there are various scenarios how we can achieve those targets. And to have a 2/3 chance of limiting warming to 1.5 degrees, the IPCC stated the greenhouse gas emissions need to peak before 2025, so now or earlier, and they need to be reduced by 43% by 2030, and that gives you a 2/3 chance of limiting warming to 1.5 degrees. That's clearly not realistic. I mean, that might be physically possible, but there's no feasible way to actually achieve this. To limit warming to around 2 degrees, likewise, greenhouse gas emissions would need to peak before 2025. They would need to be reduced by almost a third by 2030. I would say that's also not realistically possible, but it will take longer. And there are various trajectories to get there. The bottom line is even 2-degree warming is probably unavoidable. And there is more. It is very clear that the warming we have seen comes from emitted CO2, from greenhouse gases broadly. And in fact, if you just take the well-mixed greenhouse gases, CO2, methane, nitrous oxide, and the like, and calculate how much warming they should have caused, by the time of the IPCC report a few years ago, that was already 1.5 degrees. But there are offsetting factors, and the offsetting factor is air pollution, aerosols in the atmosphere, so essentially smog that directly reflects sunlight, and it modifies the properties of clouds. The IPCC estimated that masked something like 0.3 degrees warming with a large error bar on it. So we haven't seen all the warming that we would have gotten if the air were clean. And the situation might be worse than this, because a number of recent papers have tried to estimate how large the cooling effect of air pollution really is. Here's a figure from a recent paper by Guan et al. And they estimated that the cooling due to the modification of clouds by aerosols, by air pollution, is something like 1.1 watt per meter squared in energy fluxes, with a fairly large error bar on it. That's in addition to the direct reflection of sunlight by smog. LA, for example, has gotten a good bit warmer because the air has gotten cleaner. It's of course a wonderful thing that the air has gotten cleaner, but it has led to additional warming because the smog reflects sunlight. If you put these numbers together, this translates into possibly more than 1 degree warming coming from cleaning up the air alone. So if you go to net zero emissions, it will have the wonderful ancillary benefit of cleaning up the air. That's something we all should want because air pollution kills an estimated 7 million people per year. We want the air to be clean, but cleaner air will lead to, it may lead to something like 1 more degree of warming just in itself. So if this is correct, and this is ongoing research, we don't know if it's correct, but it may well be, we would see probably 2.5 degrees of warming, possibly more. This paper from which these numbers come, it used ship tracks. What you see here in the figure, these are ship tracks. That's tracks of ships over the ocean. You see where ships have passed over the ocean and have emitted sulfur dioxide primarily. It leads to formation of cloud bands that you can see in satellite image as well. They use that as a unnatural experiment to estimate the effect of aerosols on clouds. So the best case scenario, we'll need to learn to live with about 2 degrees global warming, I think probably more. How much more? Well, depends on policy pathways and the like, but probably a bit more at least. And 2 degrees global warming, again, means this is more warming in various parts of the world. For example, in the Arctic, 2 degrees global warming would mean 5-6 degrees warming. And some of that you already see being realized in the Canadian Arctic, Alaska, and the like. Now, we use global warming as a proxy for the impacts of climate change, and it's actually a pretty good proxy. You have to keep in mind that the local warming is different, but just about any climate impact that you look at, severity of storms, severity of rainfall, scales with the global warming. So it's not actually a bad proxy to look at when we talk about climate change. So while I emphasize the warming, what causes losses, economic losses, losses of property and life, in the end, is probably intense rainfall more than the warming in itself, but that scales with the global warming. So it's a useful quantity to look at. So the unavoidable conclusion is that climate change is happening and we must adapt. We must mitigate whatever warming we can, but there is more warming coming, and we must adapt to what this new normal will be. Here's one example, Hurricane Harvey in Texas in 2017. It was clearly devastating for Houston. There are three separate studies that estimated that the warming that has already occurred over the recent decades tripled the risk of that rainfall intensity occurring during Hurricane Harvey. And we climate scientists as a field, in some ways, this exemplifies how we have worked. We say, well, it's warming, it's greenhouse gases. Now there was a storm, and after the fact, we could say, well, the probability of that devastating rainfall occurring was tripled. It would be far more useful to say, before this happens, the risk of these types of events happening is so and so large, and that we haven't done as well as we could. Harvey is a good example because rare events tend to dominate the economic losses. Here is a figure from a paper by Kerry Emanuel, who's an expert on hurricanes, tropical cyclones. And the left figure shows the exceedance probability versus the loss. And the loss here is expressed as a fraction of the world domestic product. This is over the library of tropical cyclones. And what you see is that the more damaging events to the right, where the loss increases, are of course the rarer events. In the left curve, the median at the 0.5 probability sits at 2.7 times 10 to the minus 7 of the world domestic product. And you can convolve that loss curve now with the probability of occurrence of the events to get the right curve, which is a loss density. So the vertical axis gives the probability of a given loss, and the horizontal axis is the same fraction of world domestic product of the loss. And there are two things you can read off pretty much right away. You can look at the mean event loss. It is 4 times 10 to the minus 6 of the world domestic product, so it's an order of magnitude larger than the median loss. And the greatest contribution to the annual loss comes from the peak of this probability density function. And that sits at 8 times 10 to the minus 5 of the world domestic product, so yet an order of magnitude larger. The events that cause these losses, where the probability peaks here, they have roughly a 65-year return period. There are questions of resolution in the data set, but as a rule of thumb, the events that cause the greatest losses have a return period of roughly 100 years. And that makes some sense if you think about it. Events that occur frequently, we are well adapted to. Annual rainfall extremes, we built our infrastructure to be resilient to that. And the probability of extremely damaging events that say have a 1,000-year return period, the probability of those events occurring is quite small. And so somewhere in between lies the largest loss, and it turns out to be an order 100-year return period. So what this means for us as climate scientists is that we need to assess risks, especially of rare events, especially of events that have roughly a 100-year return period, and do this well. And we need to adapt to whatever that is. Of course, a 100-year return period event 50 years ago is something entirely different from 20 years from now. Rainfall intensity increases with increasing temperatures. So there's a large benefit to adapting and adapting early. And there was a nice report by the Global Commission on Adaptation a few years ago that estimated the benefit-cost ratio of various adaptation measures. For example, strengthening early warning systems had benefit-cost ratios somewhere between 3 to 1 to 13 to 1, making infrastructure resilient somewhere between 2 to 1 and 10 to 1 or so. And there was a long list of measures they went through. The point is that the benefit-cost ratio of all these measures is larger than 1. It always pays to adapt early. And the challenge for the climate sciences is that you need to know what to adapt to. If you want to make infrastructure resilient, you need to know what to make it resilient for. How high do you want to build the seawall or the stormwater management system? How large does it need to be, and the like? And there lies the problem. We don't have that information right now. Borrowing from Martin Luther King here, tomorrow is today. There's a fierce urgency of now. there's a number of reports and papers in the past few years that's stated quite eloquently what the problem is. It's a paper by Fiedler et al., Nature Climate Change, that said calls for the integration of climate science into risk disclosure and decision-making have leapfrogged the current capabilities of climate science and climate models by at least a decade. And then the PCAST report was already mentioned. It started out with saying that reliable information is critical for American families choosing where to live, municipal leaders developing flood control plans, or insurers selling wildlife coverage. And yet, when it comes to assessing the future risks from extreme weather, America is flying blind. We have climate models that have accurately predicted the global warming we have seen, and they're quite good at that, but they have not accurately predicted risks such as Hurricane Harvey occurring. You can see what the problem is. There was a figure I made a few years ago, published a few years ago, and the related figure appeared in the most recent IPCC report and a technical summary that I think summarizes the problem quite well. So each line here is a climate model. The two colors are two different emission scenarios, a higher emission scenario in orange and a lower emission scenario in blue. And you can just put any horizontal line through here, say at the 2-degree warming threshold, and look when these various models cross that 2-degree warming threshold. And the first thing you notice is there are some models where this 2-degree warming threshold was crossed a decade ago or so. Well, that's clearly wrong. And to the IPCC's credit that's in here, you can see their models are clearly not consistent with the data. But then there are models over here, irrespective of the emission scenario you look at, where this 2-degree warming threshold will only be crossed by 2060 or 2070, and anything in between. So this is just for global warming. Just for global warming, our uncertainty of when a certain temperature threshold will be crossed is about a human generation, maybe more. That's not useful for engineering purposes, for planning purposes. You need something more accurate. And then projections of the very events that you really need to get right, they're even more uncertain. And there are various reasons why climate models produce different climate outcomes, but one stands out. The by far dominant reason for the divergence among climate models is how climate models predict clouds will respond to global warming. And the main clouds that are in question here are low clouds, especially over tropical oceans. What you see on the lower right, again, you see some ship tracks crisscrossing through there in the stratocumulus field. The dynamical scales of these clouds, so the turbulence sustaining these clouds is 10 meters or so in scale. Climate model resolution, typical right now is 100 kilometers, going towards 10 kilometers, but orders of magnitude away from tens of meters. And as a slightly technical aside, you may think, say, once you go to 1 kilometer to 10 meter, that's not that big a gap. It's a huge gap because the computational effort scales with the 4th power of the resolution. So for every factor 10, or 3rd power if you only consider horizontal resolution, if you only consider horizontal resolution, for every factor 10 in resolution, you need 1,000 times the compute. So getting to tens of meters is not going to be feasible for decades into the future. So we can't compute ourselves out of that problem. And it's even slightly worse. So this is just the turbulence in clouds, and clouds consist of cloud droplets, ice crystals, and the like. They have scales of micrometers, nanometers. And what we have in the climate models are large-scale variables resolved on the model grid, say tens of kilometers, temperature, humidity, and the like. What we really want to know is what is the albedo of clouds, what are the optical properties. And the only way we know to get from the large-scale variables to the large-scale optical properties is through a myriad of tiny scale processes of droplet formation and the like that we need to model. It's the field of microphysics. This also is where aerosol enter cloud physics. And there's no way to resolve this computationally in any of our lifetime. And we just need to find a way to bridge the scales from these tiny scales, micrometers, to the large scale. And brute force computing is not going to do it. There are claims that brute force computing will help. And I mean, any increase in resolution, no question, always helps, right? There are large European efforts trying to build a CERN for climate models. They want to build models that have resolution in the kilometer range. It helps. The challenge is that, well, you still not resolve these low clouds over tropical oceans that have smaller dynamical scales. You still do not resolve the microphysics. And you cannot run these models often enough right now to learn from data, calibrate them with data. I think this is probably not the way to solve the accuracy problems. It helps to have high resolution simulations and have a few of them, but it's in itself not going to solve the problem of model divergence and inaccuracy in climate predictions. Here's just one example, and the only slightly more technical figure, bear with me. This shows 3 quantities that are good quality metrics of climate models: precipitation, long wave, and short wave radiation at the top of the atmosphere. For in the left block, there are 3 generations of climate models, CMAP3 to CMAP5, so it's roughly the last 20 years of climate modeling. And the quadrants here show the RMS error for different seasons. So it's March, April, May, June, July, August, September, October, November, December, January, February. But all you really need to know from this plot is that red is worse, blue is better. Red means larger, blue means square error, blue means smaller, blue means square error. And what you see is that over these 20 years, climate models have improved incrementally, something 10% per decade error reduction, and that's something. But if you look at how large the errors are at the bottom, these are the median errors. They're still in energy fluxes, 12, 18 watts per meter squared. The reference number you want to keep in mind is that doubling CO2 corresponds to 3.5 watts per meter squared, roughly in energy fluxes. So these errors are still large compared to the perturbation coming from increased CO2 concentrations. And the middle block shows some higher resolution simulations. They're in the 25 to 100 kilometer range. They're better than these cores of resolution. But then on the far right are simulations at kilometer scale resolution. And they're shorter simulations because they're computationally so demanding, you can't run them for long. So one should compare them with shorter simulations and what's labeled AMIP here. It's shorter averages from this. And the point is that at 1 kilometer resolution, some things maybe get a little bit better, some energy fluxes, maybe not, but some things are actually worse than what you see at 100 kilometer resolution. So resolution itself is no panacea. It helps, and we should pursue high resolution, but we shouldn't hope that this solves the problems. So I think what we really need is get climate information in the hands of end users, end users being governments, private sector, consumers. And you can think of there being a value chain that extends from climate data to something that users can use. And I think there are 2 gaps in this value chain. Number one is between data and climate models. So right now, we use data. We have an abundance of Earth observations, 50 terabytes per day from NASA alone. And we use the data mostly after the fact to evaluate how good a climate model is. We use some to calibrate climate models, but only in a very limited way. So there's a large gap between the data we have and how they inform models. And then there's a second large gap between what models produce and what end users actually need to make this useful. We write IPCC reports. I think they're great as a statement of the community, but giving someone a 4,000-page report doesn't help you plan the stormwater management system for Philadelphia. So you need to meet people where they are in their processes, and that's the second big gap. I want to talk about the first gap a bit more and the second gap towards the end as well. I'm leading this consortium called CLIMA, the Climate Modeling Alliance. It's scientists at JPL, at Caltech, and at MIT. What we're doing is we're building a hybrid physics AI or system model. The idea here is that we have a ton of data about the climate system, and we want to use it. We want to learn from these data directly as we can. So what we're doing is we're building an Earth system model that's all new. It's a scary proposition. I mean, a typical Earth system model is millions of lines of code, and you start with nothing. You started with nothing. 5 years ago. We have something that works now. So that's gotten through some tunnel there. This Earth system model, it has physical, biological, chemical components, not too different from most others. But what's a bit different is that wrapped around it is a layer of data assimilation and machine learning tools we have developed that allow us to learn from Earth observations, satellite observations, or observations from the ground, or gliders in the ocean, and also from high-resolution simulations. I'll show you an example of those in a moment. The hope that in part is realized now is that by using data more extensively, you can help bridge the scales that we can't bridge computationally to achieve greater accuracy in climate modeling. And importantly, this is, what is it not? So it's not brute force computing. It is not blindly throw all data at it and hope for the best that we learn something. It is a hybrid approach that bets on building on domain-specific knowledge. The reason here is several-fold. One is that building on conservation laws of physics and the like reduces what you have to learn from data. It reduces data demands. Ultimately, we need to predict the climate none of us have seen. We don't have data for the future. And that makes this a hard problem from a machine learning point of view. And again, using domain-specific knowledge is the way we achieve generalization here. We want to use diverse data, observations, high-resolution simulations, anything we have simultaneously. And I can sketch briefly how we do it. And the reason we wrote an all-new model is in part to exploit modern computing architectures, especially supercomputers with GPUs or other accelerators. And that's clearly the future of computing. It requires different programming styles and the like. And starting from scratch was an opportunity to design code that from the outside runs well on those machines. It's absolutely critical, I think, that if you have a data-informed Earth system model, that it satisfies 3 requirements. Number 1, I already mentioned, generalizability out of sample. The data for the future are extremely scarce. Predicting climate change is the paradigmatic out of sample, out of distribution prediction problem. So we need to predict the climate we haven't seen. Ultimately, we want people to use the climate information we provide, and that means they need to trust it. And trust is a difficult concept, but I think one element that will help in trust is if what we produce is interpretable, that there is a causal story you can tell how you get from greenhouse gas emissions, say, to certain climate impacts. Interpretability is important. Just a black box will be fine for weather forecasting. If you have a weather forecast, you know, every day you get a forecast and you have a few weeks of trying it out. And after some time, you feel like this is pretty accurate. You probably don't care how exactly it's done, and that's okay. But for climate prediction, where the verification is much harder, happens on longer timescales, the interpretability is important. A black box probably wouldn't do. And we want it to be used for engineering purposes, so uncertainty quantification is also important. So we need to broadly explore and quantify risks for climate change adaptation purposes. And without getting into technical details, our bet on how to satisfy all those requirements and make progress is to combine the best of both worlds from deep learning and reductionist science. If you want to reduce the success of deep learning to one concept, it's overparameterization. In the very successful large language models and the like, the number of parameters far exceeds the sample size, typically. And that's a regime where traditional statistics tells you don't go there, but it's a regime that has proven to be extremely successful for machine learning. However, it leads to extremely data-hungry methods, and it makes generalizability out of the distribution, interpretability, and uncertainty quantification really difficult. Reductionist science, if you want to reduce its success to one word, I would say it's parametric sparsity. If you think of Newton's law of universal gravitation, it's a one-parameter law. It's a few variables that explains how planets orbit stars or apples fall from trees and the like. It's extremely interpretable, spooky action at a distance notwithstanding. Uncertainty quantification is straightforward, right? It has been extremely successful. But if you take a complex system, the Earth system or the cloud, or just the cloud, right? To have a description of the cloud on the level of Newton's law of universal gravitation seems extremely hard. I mean, many have tried, I have tried. In complex systems, this approach seems to reach its limits. So what we do in Klima is use reductionist science as far as we can go, use coarse graining, homogenization approaches as far as we can go, and then learn the rest from data, ideally in ways that is climate invariant, that you can use data from the climate now to learn about universal processes, much like you can learn about gravitational constant from a few measurements, and then it generalizes to other parts of the solar system or other solar systems. So here would be a point where I usually would go into lots of equations and show you how it actually happens, and I'm not going to. Just to say what we do is much of our time is spent on advancing theory. Now increasing amounts of time are spent on harnessing diverse data, and I'll show you some example of the data, and we leverage computing power, and I'll show you an example of how to in a moment as well. So data for us is Earth observations. You know, Amy Braverman was here. She showed you a number of NASA missions and Earth observational data. This is NASA data from CloudSat, Calypso, and MODIS combined. So these are instruments that measure clouds from space, cloud radar, cloud red lidar, and optical measurements. And they give us for the first time a 3D data on clouds. They don't tell us everything we want to know about clouds. It's still hard to see inside clouds, the turbulent structures and the like, but they do give us a lot of data we can use. For building a climate model, you do need to know what's going on inside the cloud. And we augment observational data with high-resolution simulations that can provide additional data that tell us in more detail, say, what's going on in the cloud. Here's a simulation of clouds in the Caribbean. It's modeled after a field campaign. Blue is rain, gray is a cloud. And this is just a simulation that uses Newton's laws, the laws of thermodynamics to simulate clouds. It's the microphysics still has to be represented in simpler ways, but the dynamics are accurately resolved with a resolution, in this case, of 5 meters. So we can simulate clouds with 5-meter resolution, just not globally. You need to do it in smaller boxes. This box here is a few kilometers on the side. And we have generated hundreds, going on thousands of these types of simulations that we now use to calibrate the climate model with. So what we do to learn from these diverse data is to focus on what matters for climate, which is different from what matters for weather. For weather forecasting, you care about the state of the atmosphere tomorrow or a few days from now. For climate, you care about statistics of states of the atmosphere. Average temperatures, variance of temperatures, exceedances over extreme thresholds, and the like. So our loss function consists of statistics of the climate system, and that we minimize. What it does is it treats machine learning as an inverse problem rather than as supervised learning of input-output maps of, say, input being temperature, humidity, output being cloud cover. We don't have those inputs and outputs labeled data in the language of machine learning from observations. We have statistics of cloud cover, and we use that in an inverse problem setting to learn machine learning models. For those who know a bit about the great progress made in weather forecasting in the last 2 years with machine learning methods, in weather forecasting, you can be very successful learning input-output maps in a supervised setting, and this has been very successful. One problem all these models have is they're not stable. They're great for predicting weather a few days out, but they're not stable forever. Blow up at some point. For climate is what John von Neumann called the infinite forecast. You need to run it forever for hundreds of years. This approach ensures that the models in the end are stable, which is important. There's a downside to it. It's extremely computationally expensive, and we spent a lot of time on reducing the computational costs. We're successful in doing so, reducing computation cost by a factor 1,000 or so by combining machine learning with data assimilation ideas. I won't get into that. But let me give you an example of the statistics I'm talking about. So this is sea ice cover in the Arctic. Black is observations, and the arrows show roughly how much sea ice is expected to change in the next 50 years or so. And the colored lines are climate models from the CMIP5 generation a few years ago. And you see, this is just a seasonal cycle, January, February through January again, over the last 20 years. And well, you would think that climate models can reproduce the seasonal cycle of sea ice cover, but by and large, they can't. There are almost factor 2 variation in sea ice cover among climate models. And the variations among models in simulating the present climate, not even the future, they're larger than a climate change signal that we want to predict. So in fact, if you look at different models and ask, how long will it take before the Arctic is ice-free in summer? The main factor controlling when the Arctic will be ice-free is how much ice the model has to begin with. Models with more ice, it takes longer to melt it all. Summer, pretty straightforward. So a lot of the uncertainty in that prediction comes from biases in this state right now, in the state of the present climate. And that's an opportunity. You can drive those biases to be small by learning from data. And hopefully that will give you models with greater predictive power as well. It's a hope, it's not a theorem, right? But it's at least nice to start with a model that matches the present climate well. So just maybe 2 quick highlights of what we have done. The MIT group has developed a new ocean model. It's the fastest ocean model in existence now. It's about 10 times faster than state-of-the-art models, mostly thanks to actually rewriting it from scratch and exploiting accelerators, GPUs very effectively. So the nice thing about that is that weather in the ocean is this mesoscale turbulence that you see here, all these little eddies in the ocean. It's like the weather system in the atmosphere. They're just smaller in the ocean, but they're important for controlling the ocean circulation, mixing in the ocean. And it has been a long-standing problem in coarser resolution models to parameterize, represent these small-scale features in terms of large-scale features we can resolve. This model is so fast, we can resolve this explicitly. So there's one problem that actually is solved by resolution, which is this mesoscale turbulence perturbation problem. We can routinely run 1/12 of a degree resolution ocean simulations now. And there are other things that still are uncertain, even smaller scale processes, but at least the mesoscale we can resolve quite well. In my group at Caltech, we spent a lot of time on the cloud problem because that is the biggest uncertainty in climate models. And we built a physics-based unified models for clouds and turbulence that for the first time captures all of Earth's cloud regimes. And there are a lot of technical innovations in it. And let me not go into those, just to say that blue here, so this is height, this is a stratocumulus cloud off the coast of California. Virtually all climate models underestimate stratocumulus clouds. Here's a good typical climate model in gray, has a cloud fraction of 50%, when in fact it's closer to 100%. That's very typical. And the blue is a high resolution simulation, sort of the ground truth here, the stratocumulus cloud. And red is our new model that is, you can quibble. There's still some issues with the height of the cloud base, perhaps, but it gets the cloud fraction right and very accurately. Overall, we see roughly a factor of 3 error reduction relative to the state of the art. And this new model is the high resolution simulation is what I showed you. It's extremely high resolution. It has millions of degrees of freedom. It takes long to do that. This new reduced order model that is within the climate model is about a factor 10 to the 8 times faster than the high resolution simulation and has comparable accuracy nonetheless. So what we are doing here is beginning to close this first gap from data to climate models and reduce the errors in climate models. And I mentioned there's a second gap to making climate information actually useful and accessible to a broad range of users. That's a problem that requires AI as well in ways I'll outline. And of course, it's a problem in user experience, user interface designs that goes beyond what an academic project can do. The PCAST report was already mentioned, and I think the PCAST report mostly deals with the second gap, and I want to outline what the recommendations were. This is about policy and regulation, and there's maybe some pieces here that are of interest to folks here. There were 3 central recommendations in the PCAST report. Number 1 is the national effort to quantify extreme weather risk, climate risks, and that feeds directly into what I just showed you. Number 2, build an improved ecosystem for climate risk assessment. And 3, come up with a national adaptation plan to mitigate those risks. I'm going to talk about each one of those in a bit more detail. So I showed you we are building a climate model that will have reduced errors. There are many other climate models. The standard way to explore possible climate outcomes is to create what's called large ensembles of climate simulations. And large is in the eye of the beholder. Large for climate scientists is 100. About 100 simulations is considered large. If you're a risk modeler at a catastrophe risk firm, large would be 30,000 for hurricanes, number of hurricanes simulated. So 100 is pretty good for the global scale models, but ultimately you have to get to the smaller scales, and I'll come to that. So here's just an example of a large ensemble of various climate models in different colors. And each climate model run was started with a slightly different atmospheric initial condition sometime in the 19th century. And because the weather is chaotic, the errors of the initial condition grow. And for each model, you have this shaded band of possible outcomes. In this case, this is precipitation over the upper Colorado River basin. And you see that for each model, there is a pretty broad range of outcomes once you look at any location like that. And then there are large differences among models. In some models, the Colorado River basin will dry. In some models, will get moisture, anything in between. So each model and the variation over the initial condition, they sample the chaotic variability of the climate system, quantify that. And from model to model, well, you wish that would quantify model uncertainty. It doesn't really do that because the models are not sampling any uncertainty space. That's what we want to do better, quantify the uncertainties with observational data. So the PCAST report envisions creating large ensembles at something like 10-kilometer resolution. That's feasible now, but you still need to get to yet finer scales, kilometer scales where we live. And I think the way to do that is using AI tools, downscaling methods. And what we have are medium resolution simulations, maybe 10 kilometers. We in the Klima project, we have embedded high resolution simulation in some areas. There's grid refinement in some of the US national models. But what you really want is high resolution everywhere. And the way to get it is use generative models. Is at least one way of doing it. So here's a turbulent flow problem. It's a prototype problem for precipitation. And left is a high resolution simulation. The middle is sort of a low resolution climate simulation, if you wish. It's blurry. And the right is a generated high resolution simulation, excuse me. And if you compare the middle and the right, you see that the right fills in details in the middle. And it does it in much the same way that ChatGPT fills in details when you prompt it to do something. It uses the same mathematics behind the diffusion models. And it becomes a very fast way of generating high resolution. It's about, in this case, about 500 times faster than the medium resolution simulation. And you can train it at high resolution simulations or weather data. And we're currently doing it with real data. There's a few other groups, one at Google, doing something similar to provide localized weather impacts. There's a few technical challenges. ADAS downscaling that I mentioned. One thing that's, I think, somewhat underappreciated is that the volume of data created will be in the hundreds of petabytes. And if you just look at what it costs to store this data on a commercial cloud, it's in the millions of dollars per month. Currently, we have no real plan how to deal with this data volume. There is a lot of discussion within the government. There are challenges of fragmentation of responsibilities between government agencies, who should own it, who should do it. It may be an opportunity for public-private partnerships to do this well. Right now, the PCAS report says we should do it, but how to do it, it doesn't say, and you'll have to figure it out. And eventually, you like to have some ecosystem for climate risk assessments across sectors. So you have downscale climate predictions. You need to use those to drive hurricane models, storm surge models, and the like. So eventually, you like to have an ecosystem of apps that people can use with risks specific to their sectors that tells them the information they need in their planning process and the like. I think I should come to an end here. The third recommendation in the PCAS report is to devise a national adaptation plan. It says take all that information and ask, how do you address the risks? How do you mitigate those risks to infrastructure and the like? And right now, we have no comprehensive plan. Every city is on its own. And the idea here is to give people planning guidelines and planning tools, accessible tools, so that a small town mayor in Perdido, Alabama, is one example that is often mentioned, can access this information even though they don't have a large planning staff and the like, and can use it for their own purposes. Maybe what I'll do is I leave the points up here that summarize what I wanted to say, because my voice is giving out. Can have a look at it, and I'll just try to answer questions. So thank you.
Very impressive about where we're at, where we're not yet at, and where we need to head. We have time for questions. So in the back, and please raise your hands, and we'll have a microphone. And just introduce yourself if you would, please, and then ask your question. So we'll get you. There's one question way in the back. First.
Yeah, fascinating talk. Thank you very much, Cornelia Walter, Senior Fellow at Wharton. I have two questions, actually. The last one was on the slide that you just showed about the aim for an eco-environment to monitor climate changes. And I was wondering, is the plan also to close the feedback loop? So it's not just about getting the information, but then also to influence people to do something with it. And then the second question is about a slide that you showed relatively at the beginning, which is about it will get worse before it gets better. So that actually cleaning up the air will lead to more warming. And I'm wondering, is it ever getting better, or does it actually mean no matter what's going to happen, it will just be bad or worse? Thank you.
Now, let me start with the first question. I mean, I'm generally optimistic that it will get better, simply by virtue of rapid technological evolution. I mean, if you just look at the cost of solar power alone, right, it has dropped by an order of magnitude over the last 15 years or so. And right now, in much of the world, the cheapest way to build power plants for electricity generation is build solar power plants. And that's clearly a transition point. Eventually, the future will be solar and renewable, I have no doubt. The problem is there's a lot of inertia in the system. There are lots of regulatory problems. Lifetime of power plants is decades and the like, so it will take a bit. I think eventually we'll find a way to get to net zero emissions. When that is, I don't know, but I think we'll get there. In the meantime, there will be a lot of damage, especially to vulnerable communities, especially to countries that are not as rich as the US is and the like, right? And that's something we'll have to deal with. And something we have to adapt to. Interesting geopolitical questions, right? What will it imply about migrations and the like? That's an interesting question in itself. Your second question about the social aspect. So what I want is that sometime soon, every one of you will be able to access climate information, information about climate risks, just as easily as you access a weather forecast right now on some app that you can play with and just explore. I mean, today is an unusually hot day. What will it be like 10 or 20 years from now? Last year was not quite, but almost 0.2 degrees warmer than years before in the global mean. At 0.2 degrees warming per decade, that means it's just a normal year 10 years from now. Providing contextual information like that to where you are, what you're interested in, I would like to see that happen. And your question is now, how do you do this to optimally influence humans' behavior? I don't know. I want people to have the information. And in some ways, people, businesses, governments, right now there's an information vacuum. And my hope is that with better information, say, that's easy to access in the planning process for infrastructure, that people will take it into account as one factor among many others that you always take into account when you build something new, right? So, for example, you're working with a building technology company, they're interested in occupancy comfort in buildings a few decades from now, right? Buildings have a long lifetime, and you want to make sure people are still comfortable in a building 20 years from now. And this is, of course, only one factor among many in the building design, and you need to meet the building designers, the architects, where they are, that they can take this one factor into account in their usual workflow, in their usual process. And I think the design of the interfaces needs to be such that people can use the information, and then it will make a difference. Maybe that's would be my answer to that question.
So would it be fair to say that we're better at this point today at forecasting extreme weather events like Hurricane Harvey at a short-term basis to support efforts such as evacuations than to be able to forecast those kind of events at a longer time scale to support decisions about zoning laws or building codes and the kind of architectural decisions that you're talking about?
I think we need both.
We need both,
yeah,
but
need the short-term or accurate forecasts, and there I think, for
Okay.
example, these machine learning models can help. There has been a lot of progress, and you need the longer-term assessment of risks where there has been less progress.
right, less progress. Okay. Yes, in the black sweater there. Yeah.
Thank you so much. This is very interesting. My name is Bao-Ying. I'm a second year MBA here. I have a question because what you mentioned here, there are really big questions, really require a lot of computing power, requires a lot of resources. I just wonder, where do you see startups can play this space?
That's an interesting question, actually. It's something I've thought a lot about because you need to think about the future of Klima. So when we started this project, it was the conversations I usually had with our funders was saying eventually there is a commercial case to be made here. There is a business opportunity. 2018, that really wasn't on the horizon. Times have completely changed in these 5 years. So now there are hundreds of startups in this space. Most of the startup ecosystem is driven by the proposed SEC rule to require climate risk disclosures by publicly traded companies in the US. It's an estimated $40 billion a year market. And a lot of these startups are being acquired by rating agencies, S&P, Moody's, and the like, because they want to be positioned to, I suppose, influence whatever regulation comes. All of these startups, what they do is build some front end to the CMAP archive, the archive of existing climate models, and then provide some localized information, downscale it in some fashion. But there is not one that tries to make these climate models better. It kind of uses as input the climate models that we know are rather inadequate for the task. So you can question how good the output is. It is a bit of a wild west out there. It's unregulated. You can put this information out there, and because it's climate, you can't verify it on short time scales. I think the challenge, say, if we would want to start a company, the challenge is that what we do is we really want to get the climate predictions right. It requires larger computational resources than some regression model on top of a CMAP archive does, and cost is higher. And it's not entirely easy to make the case that what you get is actually better because it takes a while to verify it.
Okay,
That's where we are. So.
Question over here.
Yeah, thank you. It's super interesting because I'm Federico from Eolian. It is a climate tech startup, and we exactly do this. So we are trying to close the gap, and we use like the same technology that you use, so Earth observation and machine learning. It was super useful, like for simplifying computational cost and all this kind of stuff. But one problem that we are seeing and experimenting right now is that we are in Italy, and the market is so new that it's absolutely difficult to build the trust in this kind of solution, even if we backtest our models and it's like much better than everything that has already been like published by so many research centers around the world. So my point is, how do you think it's possible in a certain way to close this gap, even if there is also a business need for this kind of solution?
Yeah, I mean, you name the struggle, right? I think for me, the answer right now is maximum openness and transparency. That we are at a university, an academic project, our code is public. Anyone who wants can scrutinize it up and down. And I think that will help, right? Because there isn't sort of any one prediction target that you can take and say, I do better at this, hence my model is better. You don't have that for climate. There are, I mean, maybe seasonal, sub-seasonal, maybe there's El Nino forecast, but even that is all quite rare. I think transparency is important, for building trust, and this interpretability part, right, that you can tell a causal story, I think is crucial. But you named sort of the crux of the matter in this space, right? If everything you do is open and transparent, where's your business case? It's also difficult.
Okay, way in the back, there was a hand up in the very back row. Before? Yes, did you have your hand up before?
Thank you for the fantastic lecture. I'm a PhD student in city planning. And I have a question. I noticed your last slide, your vision stops at the decision-making step. What do you think of like evaluating these adaptation actions or policies? Like how to measure their effectiveness? Thank you.
How to measure their effectiveness? I mean, for mitigation, it's easy, right? Emissions reduced. For adaptation, you could adapt similarly sort of straightforward metrics as in life years saved. If you can measure that with appropriate counterfactuals, that might be one way of doing it. So how many lives did you save with this measure by, say, building larger levees in New Orleans or anything of that type? Yeah, I think that's what I would say.
Okay, we'll come into the front here.
Thank you. This has been great. I'm also in the planning department, and I think specifically about modeling climate stuff for small cities that don't have a lot of resources. And one of our big concerns is path dependency and the fact that we don't necessarily have 10 years, 20 years to wait for these new models to come out. And oftentimes we're working at resolutions that are less than ideal, but we need to inform policy decisions that are happening right now to protect people in the future. So I wonder, from your perspective, building these very sophisticated models, what are some of the criteria that we should look for around what constitutes good enough data, right? Things that are reliable enough, certain enough for us to drive action, even if they're imprecise.
Yeah, I mean, that's what I think about every morning I get up, that this is, usually in academic research, you can take your time, figure it out, but here you really can't take your time. You need to figure it out fast. I mean, if what you're interested in is, say, extreme rainfall, what's the probability of exceeding some threshold for which you design your system? I mean, you can probably use products like from Eol or other companies. I think for the next 10, 20 years or so, this will probably be adequate. I don't quite know what you're doing, but what many will be doing is take existing climate models, see how well they do reproducing the metric that matters for you, say, extreme rainfall intensity, weight them in some ways, weight the ones that are better more than the others, and then use some kind of regression model, machine learning or not, to scale it down to your local data with existing weather data. I think that would be sort of the common workflow. That is probably what you're doing, right? Something along those lines.
Okay, and then we'll go work our way back to brown sweater.
Hi, thanks so much for your talk. It's very, it was clearly presented and I really enjoyed it. I have a little bit of a technical question, which is I'm thinking about, so the figure where you showed, I guess it was observational data and then low resolution simulations, and then the AI generated high resolution simulations. So if I'm understanding correctly, you're solving a little bit of the parameterization problem by using AI to fill in the higher resolution features of the simulation. And so I have a question about, one is the intention to have utility in predictions on lower, on higher resolution, in which case, are those not like, is there utility in those resolutions in terms of like local communities? Is it not just a sort of hallucination of what would look correct, but not necessarily at that scale, accurate prediction? And then if I can, the sort of a second sort of backing out to longer term modeling utility, it's not obvious to me how it solves the out of sample problem. And if you could just make a comment on that.
Yeah, so there's several layers of things. So number one, the hallucinations. So we were pretty careful in designing these models that they satisfy certain physical constraints. That helps. And they were designed especially such that extreme value statistics are reproduced well. And this was just a computational example where we had computational ground truths to make sure the model does that well. So we're pretty confident that these are not hallucinations. It reproduces, especially tail events quite well. This was work done by Catherine Deck and Toby Bishop in my group, and they have some papers on how to do this. There are various technical pieces to it. The out of distribution problem, yeah, I glossed over how this really works. This is the part where equations are useful, but let me just try to tell you how it works. So for clouds and turbulence, you start with Navier-Stokes equation, and you coarse grain them, and we do it in a specific way, something called conditional averaging, where you average separately over more coherent structures, less coherent structures, so clouds and turbulent environment. You can do this exactly. It's just a math problem to solve. Once you have done that exactly, you end up with a set of equations that is reduced, but it has stuff on the right-hand side that you don't know what it is. So for example, we have average over clouds and the environment of clouds, and there is turbulent mass exchange between the cloud and the environment, something called entrainment, detrainment. Turns out to be one of the most critical parameters for controlling the cloud response to climate change. And this entrainment, detrainment, you cannot measure directly, but not in observations, it's hard even with simulations. But what we do is we reduce entrainment, detrainment to functions that we have reasonable hope to be universal. So you non-dimensionalize it, it becomes a function of a non-dimensional group. And that function is sampled well in the present climate. And I think you have legitimate reason to think that that fundamental process is not changing. It's not out of the sample that we can observe in a changed climate. And so by reducing it to these fairly small scales, universal function that you learn, we achieve generalizability. We can show it actually works in simulations, train on cooler climate, it generalizes to warmer climates. And that's kind of the crux of the matter. But again, I think also here, the simple answer is there's a lot of physics going explicitly in there.
Okay, we've got time for just a couple more questions here in the front.
Thanks a lot. My name's Paul Thompson. I'm a passive house architect here in Philadelphia. Probably know we use energy models to predict future energy use in a building, which, as you mentioned, human behavior can really throw out, has a much bigger impact than modeling does, or it can. So one of the things that we do is, if we're designing something in Philadelphia, we might use DC's weather to say, what's it going to be like in, choose a number, 5 years, 10 years, or maybe even shorter than that, to try to predict how does the building work depending on a different climate input. My question is, using your models, you paint a not very rosy scenario, like basically we're screwed no matter what happens. Could you, or have you looked at using your model to say, what if we seeded the atmosphere or had a big solar shade that shaded the earth, sort of a large intervention that changes the whole reaction of natural processes on the earth?
Yeah, it's a good idea to use DC data for Philadelphia. So we're working with a company you probably use these typical meteorological year files, right? So we're trying to provide them for the future, and also in a way that it's not just typical, so not just the mean, but that it captures, say, typical heat waves, if you want to call it that are not in the mean, but can happen. And we hope to have that. And I hope this would be something you can easily use them, because it's just the same files that you're already using just for Philadelphia for the future. To be asking about geoengineering, a lot of people ask about geoengineering. I mean, yes, we haven't done that with our models. We could. One day we will study geoengineering scenarios. A lot of people are doing that. So you can inject aerosols in the stratosphere. They reflect sunlight. It will lead to cooling. That works, I think, pretty much without question. I think it's pretty clear what the impact will be. There are bigger questions about seeding clouds. That's probably more difficult, but there are experiments ongoing, marine cloud brightening projects. It's hard to explore that computationally because models do so poorly in simulating those clouds. I think the challenge with all these approaches is that suppose we actually do this. Suppose we inject aerosols in the stratosphere. We can do it. It will mitigate some warming. Suppose you do it for 20 or 30 years or however long. And for some reason, then this ends. I mean, geopolitical instability, lack of agreement of getting, say, for aerosol injector in the stratosphere, you would need to inject aerosols every few months, shoot rockets or high-flying planes in the stratosphere. And for some reason, you miss it for a while. These aerosols will deposit out. They settle out pretty quickly, timescale of a few months. So you will see all the warming that you have avoided until that point within a few months or a year timescale. It's called the termination shock. It's a huge governance problem.
You need to be reliably administering that. Interesting.
Yeah, technically it's doable, which is why so many people are so interested in it. But there's a moral hazard, there's a governance problem, and those are thorny issues.
Any more durable particles that you wouldn't have to, that you could use that?
No, I mean, eventually anything will settle. I mean, the stratosphere is quite good because it takes a long time. Anything you do for marine cloud brightening, seeding clouds near the surface, that's a very short time scale. The particles settle. Stratosphere, at least you have 6 months or so.
Okay. All right. In the far back.
Hi, thank you. I'm curious how you think about the potential for these new models to interact with the economic side of climate modeling in terms of being able to integrate into integrated assessment models where you're thinking about the interaction between climate and the economy. Because my limited understanding of that space is often you are using like the most very, very often very reduced form models of climate, but then we rely on that for these large scale economic predictions of damage. So I'm just curious about how you think about that interaction between those two literatures and what you're doing.
Yeah. Yeah, I mean, for integrated assessment modeling, you want to explore a lot of scenarios quickly. You don't want to run a complicated climate model, but I think that's where these machine learning emulators, I think, have great potential. You can build an emulator now of whatever you're interested in a climate model. It's very rapid to evaluate, and it can give you localized information, so not just the global information that's typically used in integrated assessment modeling. And I'm not sure if people have done that, but it should be happening. I think you can really do integrated assessment model with regional information, I think, quite easily and quite rapidly now.
Okay, a couple rows up earlier. We've got two more hands up to close out our time.
Hello, I'm a fourth-year material science PhD student. So about 3 months ago, Google came out with GraphCast, which was like AI-powered weather prediction, but it's only 10 days out. I was wondering, like, how far out are you looking to make these models able to predict low weather? And two, like, are you trying to look for any collaborations with these very big tech companies, which probably have like a large share of the most talented people to work on this problem?
So the weather forecasting and the climate problem are really fundamentally different. In weather forecasting, you take the state of the atmosphere right now, you project it forward in time for a few days or a few weeks. And then climate, you do what used to be called the infinite forecast, run it forever, right? And accumulate statistics. GraphCast is very successful in ForecastNet, and the other ML weather forecasting models are very successful at weather forecasting. They're not useful as climate models as they are for several reasons. A, they're not long-term stable. That's the simplest. Maybe that can be solved. But more fundamentally, for example, climate is first and foremost the problem of radiative transfer. The zeroth order problem is you change the composition of the atmosphere. What's the radiative effect of that? At the top of the atmosphere, how does it affect surface temperature? And that's not something you can learn from data directly from any observations we have, because we haven't sampled the CO2 concentrations that matter here. I mean, we have data for just a small range of CO2 concentrations in the atmosphere. From that, you won't be able to predict the response of the system 50 or 100 ppm more in the atmosphere. And you can say, well, maybe take an ML model like that and add a radiative transfer model as a physical radiative transfer model. That I think would be the next step to do it. That would help solve that problem. But there remains the problem, for example, that there's a direct radiative effect on clouds. So more CO2 in the atmosphere has a direct radiative effect on cloud cover. Something called rapid adjustments. Likewise, that's so convolved with everything else happening in weather that you won't be able to deconvolve it from data alone. I think if you think this problem through, you kind of arrive at the approach we took, which is much more process-based, and stick the ML models where the physics doesn't go any further. Am I working? Well, I'm a Google employee, yes. So I'm speaking here as a Caltech professor, not as a Google employee, but yes, I'm working with people there.
Okay, last question over here.
Hi, thank you for the great talk. I'm an economics PhD student at Wharton, and I'm particularly interested in home insurance questions. And we see that in several states in the US where climate change is a particular concern, those premiums have been increasing steadily the last few years. And I just wonder what your take is on the insurance industry and the reinsurance industry. How far along are they in this technological integration of AI processes? And do you think that potentially they're doing more harm by using outdated models than by just not looking at that? Thank you.
Yeah, there are many layers to your question. So the catastrophe modeling, which is modeling losses due to extreme events, hazards, and the like, that's done well, I think, in the private sector, reinsurance companies or various risk companies, RMS, one example. And the insurance industry is using that data they provide extensively. But there are many market failures in insurance markets. So maybe flood risk is the most obvious one, right? So flood insurance is basically federalized in the US, and it is assessed based on outdated flood maps, based on the past history, which is not a good guide for the future, and even it's not even done very well for past history often. I mean, in some ways that should change. It seems pretty obvious, right, that you want to price risk accurately, but it's politically, ethically, socially really challenging, right? I mean, just take one example. Suppose you come to the conclusion that insuring property in some low-lying part of whatever, Louisiana, doesn't make sense. It's far more cost-effective for communities to move. From a purely economic point of view, that might be the conclusion you come to in some places. But destroying grown communities, typically already vulnerable communities, imposing a great burden on them is it comes with a large cost. It's not just economic, right? And I think that figures in the whole insurance calculation. I mean, I've been part of these discussions for years of how flood risk is mispriced. Everyone knows it. And everyone who tries to change it fails for political reasons. And they're not necessarily bad reasons, because it's you try to correct the system typically on the backs of people already vulnerable, and it's obviously fraud.
Well, on that note, we will conclude, but I want to say thank you for being here to help us understand better the needs for information, the path forward to close some of the gaps in information, even if in the end some of the decisions will have to be very hard ones, but at least they should be well informed. And you've done us a great service, so thank you for being here,
For having me.
and thank you for all the work that you're doing.